Hello, students. We're in lesson 17. Hang with us. There's only 21 lessons total. We're getting very close to the end of the course. Video A. What we're going to do is we're going to continue testing proportions, except now we're going to compare two populations. Maybe we'll have a population of females, population of males, and we'd like to know which population has a higher percentage of smokers. And in fact, that's the first example. Here at the college, the author of these notes has a hunch that a greater percentage of females are smokers when compared to males. A student mentioned to me the other day, I said, which gender do you think smokes more? And they said females, and I said, why? And they said, well, because all the nursing students are always outside smoking. I said, well, there you go. I guess they're easily identifiable with the scrubs on, right? My hunch is primarily based on visual evidence from working here past a number of years. So we're going to run a test, right? In a statistics course, we have to collect some data, run a test. We could test that hypothesis that there are a higher percentage of female smokers by collecting independent samples here at the college. I'll collect a sample of females. I'll ask each female, do you smoke or don't you smoke? I'll collect a sample of males. I'll do the same thing. With the two samples, I'll get two p-hats now, a sample proportion from both groups. Determine which percentage were smokers, and here are the hypotheses that we'll test. Okay. To start, remember the null is always assumed true, HO. I will presume that P, I'll put for F for the females equals P for the males, and just a couple of notes here off to the side. Remember the null is always assumed true to start before we collect our data. And what's this saying? I'm assuming that the percentage of female smokers equals the percentage of male smokers. Right, so maybe we'll put it like percentage of female smokers equals percentage of male smokers, right? That's what I'll assume. My hunch is that there are more female smokers as a percentage. So for the alternative hypothesis, HA, P sub F greater than P sub M, percentage of female smokers is greater than. Okay. Again, we look to the problem description, try to figure out what symbol goes down here in the alternative. Now, to me, this is the easy way to think about it. I could write the hypotheses in a different way, and I'm going to do that over maybe a little bit more space over there. You don't need to write it both ways, students. One is sufficient, but I need to point something out. So equivalently, H sub 0. If I subtract everything to the left-hand side, I'll subtract the P sub M. What would I get? Proportion of females minus the proportion of males would equal 0. Right? Just subtract that over, and I get 0 on the right-hand side. And then for H sub A, proportion of females minus the proportion of males would then be greater than 0. The first way is more intuitive to me. You're more than welcome to write it the first way. The reason I'm showing you this way is because in this lesson we're testing for a difference. The difference between the two proportions. And when you think of the word difference, you're thinking subtract. And so I need to emphasize that there is a subtraction in here. It's just hidden in the more intuitive way to write those hypotheses. All right, I think it says that in those bullet points right below. If I flip this, again, you don't have to write it both ways. Lesson 17, we're testing for a difference between the two proportions. Difference means subtract. Right? Difference means to subtract. You can definitely see it in that second presentation there. All right, so that's the first step, thinking about those hypotheses. Number 2, down at the bottom of the page, we know unless we get really lucky, the sample proportions are going to be different, right? Get the ladies, determine the proportion of smokers, you'll get a p-hat. Do the same thing for the guys. Those numbers aren't going to be the same, right? They'll be different. So here Here's the data. In 120 randomly selected females, we had 30 smokers. The variable's categorical, either you're a smoker or you're not. And so how can I summarize it with sample proportions? So the data could be summarized. P hat for the females equals, let's see, it's 30 out of 120. What is that? About 25%, right? 0.25. Only 90 guys. It's okay that the sample sizes are not exactly the same. I've had that question in the past. I had 90 guys only, 18 smokers. Well, there's a lot more females at Cecil College, so there you go. And 18 out of 90, I hope, is 20%. Maybe don't write that down just yet. Yep, it is. Right, so I don't know. For the ladies, 25% smokers. And for the guys, 20% smoke. This is sample data. What would happen if you took a separate sample? This number would surely change unless we got lucky, might get 25% again. And this number would surely change unless we got lucky on repeated samples. So think to yourself, are you convinced? Remember what my hunch was? My hunch was that a higher proportion of females smoke. Does this convince you? Are those numbers far enough apart to reject that null hypothesis? Or is it too close to call? Okay. Maybe some of you think it's too close, maybe some of you are convinced, and that's fine. The thing is, we've got to run the test. So statistically, let's determine if these are far enough apart. We'll flip the page, number 3 up at the top. The main question, students, how much greater would the sample proportion of females need to be to convince you? How much greater would the sample proportion of female smokers need to be compared to that for the males for us to conclude that for the whole college, more females smoke, a higher percentage? Certainly in the sample, more females smoke, but that's not what we care about. We care about the whole school. There's probably 2,800, 3,000 students that go here. Certainly with our sample sizes, now think of these extremes. With 120 females, 90 guys, if I had 50% female smokers and just 10% males in my sample, I'd have a no-brainer, right? Everybody in their right mind would conclude that, you bet, at Cecil College, more females are smokers, right? A higher percentage. So this would be a no-brainer. At Cecil College, a higher percentage of females smoke. This is just a what-if game. What if my two samples were 50% versus 10%? Statistically, it's a no-brainer. Common sense, it's a no-brainer. The data's telling me that, Coop, you're right. Higher percentage of females smoke. Now, what's the other no-brainer? Here, pretend this happened. I take my samples again, we're playing what if here. 120 females, I got 25% female smokers. 90 guys, I get 24.4% male smokers. Does that convince you that for the whole school more females smoke, or is it too close to call? Too close to call, right? It has to be too close to call. Those numbers are not far enough apart. This is definitely too close to call. And you've got the sense of how you wrap up these hypothesis tests. You would say something like, look, there's no evidence that a higher percentage of, and again, remember, it's all females, smoke. Compared to males, blah, 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 right? Too close to call. The 25% versus a 24.4 is just like, statistically, we're not impressed, right? It needed to be further apart. Now, what was our data? Our data was 25% compared to 20%, right? Is that difference too close to call? Is that difference convincing? I guess we'll find out as we run through the test. So, bottom of the page to wrap up this first video. And by the way, it's a long one. We split it into 3 parts. You're going to get me for 3 in a row, and then Kim Shepard will be back to do a couple of different examples. the key idea, bottom of the second page. When I compare two sample proportions, I'm going to measure the difference between the two with the standard deviation or a standard error. Okay? Now, for this one, I'm going to give you the standard deviation. Here's the notation. It's the standard deviation of, let's put a p hat 1 minus p hat 2. Just enough room to fit that in, right? This is where the formulas get a little messy. I try to think of what this is. In our first sample, say I took repeated samples. Here's sample 1. What was the difference, females versus males? Didn't I have a 5% difference? It was the 25 minus 20%. What if I took a separate sample? Throw all the students back, fish out new samples of both genders. Maybe that time I got a 1.7% difference. Maybe on sample 3 there was actually more males. Maybe that time we got a negative 1.2% difference. And we would continue forever. I'm taking the standard deviation of these numbers. I'm trying to see how much variation there is in that sample-to-sample difference. That's what this is. And this number will sort of unlock, are my two samples different enough for me to conclude that more females smoke compared to males? Okay, so this is what we're taking the standard deviation of, those differences. Here's the formula. Put a P1 for the first sample. Now in our example this would have been females, right? But in general just 1 and 2. 1 minus P1 all over N1. And we've been working with proportions for a good couple of weeks. This should look awfully familiar. So, oh, I know what that is. Right? Here's a symbol here. Put the plus. It is correct. I know we're taking the standard deviation of a difference, but I do add them here, and I'll just give you a word about that in a second. And then over here, P2, 1 minus P2 all over N2. You can handle this. It's just doing the thing you know how to do twice, adding up the results. Okay. Now, one word here. I know I'm taking the standard deviation of the difference between two quantities, but whenever we take variances or standard deviations of differences, you actually do add the individual components here. So this is why there is a plus. It may seem like it's a typo, but it's not. Okay. Now, this formula is sort of in the theoretical world. I'd love to know P1, but I really won't know that. Right? At the bottom you can see, and I'm going to keep this slide up, but on the bottom of the sheet, this formula assumes that we know the values of P1 and P2, which we won't. Right? This P1 would be the true percentage of smokers for all females at Cecil. I won't know that. This is sort of the population that I'm investigating. And the P2 would be the true proportion of smokers for all the guys, all the males at Cecil. Okay? So, we've run into this problem in the past. I'd love to know the standard deviation. It would sort of give me the exact answer, but I'm not going to get it. So the problem is standard deviation is kind of out, and we're going to have to use a standard error, but that's the topic of the beginning for the next video. So we'll pause for a second, grab yourself a Coke, come back in 2 minutes, and we're going to pick it right back up with the same example. Thanks.